This is a video about the A-level chemistry topic of infrared spectroscopy, which is part of the organic analysis topic. Infrared spectroscopy is another analytical technique that can be used alongside mass spec and test tube reactions to figure out the identity of a substance. Like test tube reactions, it's used to identify the functional group, so that's the group of atoms that are responsible for that molecule's chemistry. So the first thing that we need to know is that infrared radiation is absorbed by any polar bond, and when that light is absorbed, it causes the bond to vibrate. And each bond absorbs different frequencies of light. So by identifying what frequencies have been absorbed, we can figure out what bonds there are. So from a practical point of view, this involves taking a sample and shining some different frequencies of infrared light through that sample, and then looking at the light that is transmitted, so it goes all the way through, and whichever frequencies are absent, those must correspond to the bonds that are in that substance. The frequency of the infrared absorbed is not just dependent on the atoms that are in that bond, it's also dependent on where that group of atoms is in the rest of the molecule. So this is an abbreviated bit of the data sheet, and you'll see here that we have values for an OH bond in alcohols and also an OH bond in acids, in carboxylic acids. And you can see that they are in different places, and also that the thing that we see for OHs in acids is actually quite broad, and you'll really get used to identifying this in the spectrum. You'll just see that it's this really, really broad peak. And we should also say that this number, wave number, that is the frequency, and it's expressed in per centimetres. So in other words, 1 divided by the wavelength. Now you'll see that a range of about 500 is given both for carboxylic acids and also for CH bonds, but the CH bond is actually a narrower peak. So whereas the carboxylic acid peak will take up the whole of that 500 centimetres to the -1, the CH bond will be a narrower peak that falls within that range. And what we see is that in saturated molecules, it happens at the lower end, sort of nearer to 2,800, but in unsaturated molecules like alkenes, this is shifted towards the higher end of the wave number. So you're not going to get confused about which one you're looking at. And if they both occur in the same molecule, so say if you just have a simple organic alcohol like ethanol or propanol, then what actually happens is that the presence of the CH bond makes the OH peak look kind of bumpy. So what are you actually expecting from exam questions? Well, you're going to be identifying signals and the functional groups that they correspond to in the region that is above 1500 centimetres to the -1. And the reason that you're only looking at the left-hand side of the spectrum output is that there you're going to get fairly clear and unambiguous signals, whereas to the right of 1500, it's this really dense region with lots and lots of signals. It's what we call the fingerprint region, and basically it's impossible to spot anything in there because there's just too much going on. And you're going to get some questions which are numerical and just give you the numbers and ask you to look. You're going to get some questions where they're graphical and they give you the picture of the spectrum. And very often these questions are synoptic, so you're going to have other parts of the organic specification assessed within the same question. Of 1-mark questions, which you would think would be quite straightforward, but actually they're assessing quite a few different skills. So they're assessing whether you can use the data sheet to identify which functional group these ranges of wave numbers refer to, but also whether you're able to identify isomers and also whether you're able to draw skeletal formulae. So pause the video and have a go at answering the questions, and then unpause and I'll go through the answers. So in our first question, we have this peak between 1680 and 1750, and that's going to correspond to a carbon double bonded to an oxygen. So we then need to think, well, what would an isomer of propanol be that would contain that, and what would it look like? So we're going to come up with something that looks a little bit like this, and it's going to be a ketone, propanone. And then if we're thinking about a structural isomer, that has an absorption between 3230 and 3550, then that's going to have an alcohol group. So we now need to figure out what an alcohol could be that was an isomer of propanol. And so that's going to need to be a cyclopropanol. So now let's start to have a think about what do the graphics actually look like, what would you see on a spectrum. So first of all, let's just orientate ourselves with what we can see. So at the top, we're looking at percentage transmittance, so how much light is getting through. And so if the percentage transmittance is 100, that means that none is being absorbed at all. And then obviously at the bottom, we've got total absorbance. Our biggest wave number is on the left of the graph, and that's always going to be the case. And anywhere that we're seeing the line dipping down, that represents some infrared light being absorbed. And confusingly, we refer to this as a peak, even though it's clearly more of a trough, but that's just the way that we describe it. So here I'd be saying that there was a peak between 3000 and 4000. And you'll also spot that, kind of annoyingly, the numbers along the bottom do not go up in a consistent scale, which always frustrates me for some reason, but that's just the way it is. And then this region on the right hand side that I mentioned, this is what's called the fingerprint region. So this is unique for every molecule, and when you're trying to identify a molecule or a compound, you're partly looking for the functional groups in the region to the left of 1500, but also you would, if you had access to a database, you would look up the fingerprint region as well, because that is just totally different for every single molecule. And then one more thing we should also say is that this spectrum doesn't give us any information about the numbers of bonds. So I can't look at this and say, oh, that's a big peak. That means there are several of that type of bond. It just tells me about presence or absence. So if we just massively simplify this for a second so we can make it much easier to understand, I've taken out all of the fingerprint region and just left us with these two peaks. So if I look at my data sheet, I'm looking for where these peaks fall. So I've got one that's around 3000 and one that's around 1600. And if I look at that one that's about 3000, I can see that it's quite a nice narrow peak. It's not my very broad peak that I would see for a carboxylic acid. So that one is going to be a carbon hydrogen. And then this other peak that's sort of around about 1600, 1700, that's going to be a carbon-carbon double bond. So what I'm looking at here is going to be some kind of alkene. So if I come back to my original, slightly more realistic spectrum, I can see that I've got three main functional groups here, because remember, I'm not really going to look at the fingerprint region. I'm just going to talk about the fact that it exists and the fact that I can look it up in a database. So I'd be looking at this and saying, okay, so I've got one peak that corresponds to an OH in alcohol. It's not really broad enough for carboxylic acid, and it's a bit too far to the left for that. I've also got my carbon-hydrogen bonds, and I've also got that carbon-carbon double bond there. And actually, this is the spectrum for but-2n-1-ol. If I get rid of that data sheet so that you can see the fingerprint region, we can see that there is a peak corresponding to the carbon-oxygen bond, but it's just really hard to identify because there's so much going on in that fingerprint region. But what the fingerprint region would be really useful for is if I was trying to differentiate between different kinds of organic alcohol. So I know that this is but-2n-1-ol, but if I didn't know that, I would be able to look at that and say, well, this is what the fingerprint looks like if that alcohol group is on the first carbon, and this is what it looks like if it's on the second carbon, and which one of those fingerprints matches. You're also going to see questions in the style of this one, where you're asked to say whether a compound fits into one homologous series or another, and then justify your reasoning. So here we're asked about, is this one an alcohol or an alkene? So there's lots of information in this spectrum that we're not interested in right now. I could identify carbon-hydrogen bonds, but that's not useful information because both of these could have carbon-hydrogen bonds. So all I really care about is, does it have a hydroxy group in an alcohol background, or does it have a carbon-carbon double bond? So these are the only wave numbers that I'm actually interested in. And if I look here, I can see this is often quite a small peak, but I do have that peak at 1620 to 1680, so that's my carbon-carbon double bond, and therefore it's an alkene. So I'd be saying this compound is an alkene because it does show a peak between 1620 and 1680, and that corresponds to a carbon-carbon double bond, and it doesn't show a peak that corresponds to an alcohol group. This is a similar question, only this time we're differentiating between 4 different specific compounds. Now, if I was doing a different technique, if I was maybe doing mass spectrometry, I might be thinking about the size of these molecules, but infrared, of course, doesn't give us any information about the number of carbons or about how heavy these molecules are. So I need to focus on their functional groups. So here we've got an alcohol, a carboxylic acid, a ketone, and an alkene. And so I can disregard anything apart from their functional groups. So all of these have carbon-carbon bonds, all of these have carbon-hydrogen bonds, and so that's not going to give me any useful information. What I need to focus on is their functional groups. So for an alcohol, the functional group is obviously the OH, so I'm going to see the bond between that oxygen and hydrogen, but also the carbon bond to the oxygen to sort of attach that functional group. Then for the carboxylic acid, I've got both double and single bonds from the carbon to the oxygen, and then again that OH group, although it's in a different background, so the peak won't be in quite the same place and won't look quite the same. Then for the ketone, I've got the carbon-oxygen double bond again, and for the alkene, I've got a carbon-carbon double bond. So I need my list of those different bonds. I'm just going to look and see what can I find. So the first thing I do is I look out at 1620 to 1680 for that carbon-carbon double bond, and I don't have a peak there, it's just missing. So I can rule out pentene straight away. But I do have this bond at 1680 to 1750. So this is, you'll often see this when you see a carbon-oxygen bond. It's a very skinny peak, and it also goes pretty much the entire way to the bottom. It's not like that carbon-carbon double one that we saw earlier that was quite small. This is a big peak. So then I want to think, well, okay, do I have the carbon-oxygen and the oxygen-hydrogen? Because that carbon-oxygen double bond could be in butanone, but it could also be in propanoic acid. And what I see is that although I do have a bond that is maybe in the right region for OH for acids, this isn't that characteristic really fat carboxylic acid peak that we see. This is way too skinny. So this probably represents the carbon-hydrogen bonding that we see in butanone. It's not the OH group in propanoic acid. So therefore I can narrow this down, and this compound is going to be butanone. And then rather than asking you to figure out the answer, they might tell you the answer and ask you to justify why that is the answer. So why does this spectrum belong to an aldehyde, not an alcohol, carboxylic acid, or alkene? So we're going to be looking for the same things that we were looking for before, but in each instance we want to say this is the wave number we're looking at and it corresponds to this bond. So I've got absorption at 1680 to 1750, that's caused by the carbon double bond to oxygen, and again you can see this is a very skinny peak and it goes all the way to the bottom. I haven't got any absorption at 1620 to 1680, so I haven't got that carbon-carbon double bond. And I also don't have any absorption in either of the places that would indicate an OH bond. So I've ruled out both the alcohol and the carboxylic acid. And then slightly randomly, I think, we get a bit shoved on about the greenhouse effect. And I can see the relevance of this because it's all about infrared and making polar bonds vibrate, but it just seems really random in the context of chemical analysis. So we've already said that infrared radiation is absorbed by any polar bond, and this causes the bond to vibrate. And you know from GCSE that there are 3 named gases that we studied at GCSE that are greenhouse gases because they contain these polar bonds that vibrate in a bunch of different ways. And if we didn't have greenhouse gases at all, then Earth would be uninhabitable because it would just be far too cold. But having enough of them allows the temperature to be high enough on Earth that life can survive. So how does this work? Well, the sun emits both visible and UV radiation. So that's got a relatively short wavelength. This reaches the ground and it's absorbed by the ground and then re-emitted, in other words, given back out. And as it's given back out, it has slightly less energy and it also has a slightly longer wavelength. So it's now infrared radiation, and that infrared radiation is going to be absorbed by polar bonds, causing them to vibrate. And then they give some of it out again. So that radiation that's being given out again is going to cause the atmosphere to warm up, and that's what causes the greenhouse effect. So a typical little 2-mark question might ask you to state and explain how a named greenhouse gas contributes to global warming. So you just need to identify that it has polar bonds, and therefore those polar bonds are able to absorb infrared radiation, and you might want to give the range of the radiation for that particular polar bond. Thank you very much for watching, and I hope that you found this video useful in your revision for A-level chemistry. If you did find it useful, then don't forget to like and subscribe for more A-level chemistry videos coming soon.